everything is an expression of strain. So we've already had a significant experience with strain. When we look at a fold, that's strain. When we look at a fabric, a rock fabric, that is strain. When we look at fractures, that's strain. When we look at a thrust fault system, that is strain on steroids. So we've already had a tremendous amount of experience with strain. And we used this symbology here as an expression for strain. This is the nomenclature that we're going to use. That nomenclature is an indicial or an Einsteinian nomenclature for a 3x3 matrix that has some rather peculiar characteristics. It is truly a second order tensor. If you've had linear algebra, or if you're anticipating linear algebra in your near future, you will play with matrices and a subset of matrices that are truly tensors, that describe the relationships between vector fields. A tensor can truly describe the characteristics of a vector field and have a character of being ellipsoidal in nature. And so this is interchangeable. When we say strain, you should think epsilon ij. When we say epsilon ij, you should think, oh, strain. Folds, faults, fractures, all of the F words that we've used in the class. So these two are interchangeable. When we think about stress, this is going to become sigma ij, where we're looking at, again, a second order tensor, where we're looking at a 3x3 matrix that has the additional characteristic of describing a vector field and the relationships between vector fields. And we're using this as a shorthand. And so these things are absolutely interchangeable. And once we learn how to get to this point, hopefully all of the rest will make sense. So that when we say stress causes strain, you'll be thinking in terms of the symbology here.
Just to confirm, I know with stress you said that it's a way to, using a matrix is a way to relate different vector fields to one another. Is that the same for strain as well?
Yes, oh yes. When we, Tim, the short answer is a diagram. When we think about this, what we're doing mathematically is, if you will allow a slight jump forward, let's say that we have, in this case, an undeformed system at some point in time, T0. And so you can visualize that as a circle, a sphere, whatever. That is undeformed. Then we have, at some time, Tn, we have a deformed system. This line is something happened here. So time passed and something got squished. So that now this is a deformed system. If we do a really simplistic analysis, I can draw a deformation vector, a displacement vector. This point, x, y, z, at T0 corresponds to a point x prime, y prime, z prime at Tn there. This is the displacement vector. Well, guess what? We have a displacement vector field here, because every point here has to correlate to every point there, right? So now I have a displacement vector. I can look at the gradient of that displacement vector. If you've read the Tensors 101 handout, I can look at the gradient of that and then the tensor second order falls out of that. Okay? So this relates undeformed, and this basically tells us about the equilibrium condition. Stress at a point. What the stress field looks like in relationship to whatever is going on at the boundaries of our system. And so there is a very, there's a ridiculously simple mathematical basis for this. It will take us a while to work through and realize just how simple it really is. The mathematics can look scary, but the reality is that it becomes a well-done once we get through the whole process. And you know, it becomes one of those things where it's, why didn't you tell me that before? It is a very, very nice, well-behaved system. So when we look at this cause, here we're really looking at boundary conditions. What are the initial conditions? And we're looking at material behavior. Well, the way that I like to express this is KLM. It's a matrix operator. It is a fourth order tensor. And just to front load, yeah.
The KLM, what are you saying is KLM?
That is the material behavior. That is a fourth order tensor. If you are going to relate, and the easiest way to think about tensors is if I have a scalar field, I can use a vector system to relate it. If I want to relate one point to another, I need a vector. So a vector is simply a first order tensor. A scalar is a tensor of zeroth order. If I want to relate vector field to vector field, I need a second order tensor. If I want to relate two second order tensors, I need a fourth order tensor, not a third order tensor. A third order tensor is reserved for odd things like inertia. Some electromagnetics are third order tensors. So I need, this would be a fourth order system, and it reflects rheology. So we would need elastic, plastic, viscous, blah, 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 all of the behavior of materials. And so if you have had the ES class on behavior of materials, you've probably played with deriving the elastic coefficients, and you realize that this thing is for a simple isotropic body, you end up with a 6x6 matrix of actually integral equations, triple integral equations, in order to fully describe the elastic system. Plastic systems get real odd, viscous systems, if you've had fluid dynamics, viscous systems can get really kind of intriguing to relate those systems. And so this is simply the symbolic expression of stress causes strain. If you have a material, if you apply a load, it is going to deform. Duh, that is obvious. So the way it responds, the way it deforms, is going to depend on what our stress system looks like, what conditions do we have, what initial conditions, and what material do we have. And so ultimately our end game is to try to understand how do rock materials behave and why, and then what sorts of structures will develop as a response to loading. So we're beginning to look at the mechanical aspects of this, and we're starting the investigation into a little bit about stress. So we want to be stressed a little, not in a bad way. But when we started thinking about stress, we looked at how do geologists view materials, and so we went through homogeneous and homogeneous, isotropic and isotropic materials and material responses. And we looked at Newton's laws. And we want to make sure we understand Newton's laws. We started with momentum. And there were some questions on momentum on the cards. And so let's make sure we understand what momentum really describes. The basic idea is that if you have an object and you want to change its velocity, you have to apply a force. That force might be a body force, like gravity. That might be a surface force, like a traction. Now, when I say attraction, that's not liking someone. It is a space and then traction, a surface force. We expressed this as simply F equals ma, where this is an acceleration. You could just as easily have this as m dv dt. In a system, change in velocity with respect to time. So we're inducing an acceleration in a system. So what this tells us is if we were in a perfect frictionless world, let's say that I wanted to change the velocity of this table, I would have to push on the table in order to change that velocity. In the absence of friction, I could easily just touch it and it would change. But there are some consequences of that, and we need other laws in order to fully work with our system. And so we have to look at inertia. The concept of inertia is that an object at rest will remain at rest unless you disturb it. So in this case, and I'm going to take sort of a shortcut. I'm going to cheat a little bit and just point back. If you have an object at rest, you have to apply force to that object in order to get it to change velocity. There's a feedback loop here. There's a very, very nice feedback loop. An object at uniform motion will remain in uniform motion unless it is disturbed. So if we have an object moving through space, it will move in a uniform direction at a uniform velocity unless we disturb it, either gravitationally or interaction. And there, if we have an interaction, we go to classical mechanics or physical mechanics. We look at gravity. We have to start beginning thinking about relativity. But we're going to cause that object to change its velocity in that system. And so there's a dynamic feedback here. The other thing that we want to be aware of is as I push on this table, it's pushing back. There's always an opposite and equal reaction. And so we're going to call that equilibrium. basically we can think of it, if you'll allow me to do a shorthand, the sum of the forces in, let's say, the x direction is going to be equal to 0. So if I push, it's pushing back with exactly the same force. If I push on this board, it's pushing back on me with exactly the same force in a system. Now, let's think about this. Let's make sure we understand what this tells us, because we have some intriguing things that can cause confusion. Let's say that we have, let's go back to physics 1 and let's look at a classical collision. Let's say that we have two objects, a large mass and a small mass, moving toward each other at some velocity. If these two collide, so now we have, boom, a collision. Which one has the greater force? Okay. Does everybody get that?
Can you repeat that? It's equal forces.
So one that's a greater force.
The force here is the same. The masses are different, so the change in velocity will be different due to this collision. The force is equal, exactly equal, because of equilibrium. So that if we look at this, and let's say this is a perfect elastic collision, which will be traveling faster after this collision.
Well, it's elastic.
Perfectly elastic. This one's going to be moving more quickly because it has the lower mass. So if we come back here, lower mass, same force, greater acceleration in that particular system. And you can demonstrate that. The classic way of demonstrating it, and I hope they did this for you in your physics class, if you take a basketball and a ping pong ball and place the ping pong ball on top of the basketball and then drop them, what happens? The ping pong ball goes just flying off, hits the ceiling because of that system right there, because it's lower mass. Its mass is so low. So if we go back and think about the example I think we talked about in SpaceX, early days of space exploration in the orbital missions of Gemini series into the Apollo series, one of the first astronauts to try to do a spacewalk nearly died because they had forgotten equilibrium and inertia. So they were struggling, fighting to get things to move, and exhausted themselves. Their heart rate got to the point that they nearly had heart failure. And there was a discussion at Mission Control about cutting their life support line and letting them perish because they were endangering the mission. And it took a physicist to remember, after a little bit of struggling, wait a minute, I'm trying to do these things and I'm ignoring inertia, momentum, and equilibrium. So that they were able to train now the astronauts to do work in space. Because if you go up, let's say we were to go up to the Hubble Space Telescope and we started yanking around on it, well, we would move it, but we have the lower mass, so we would be the ones having some extraordinary reaction to that movement of that particular object. So we have these rules as, I guess, to go Pirates of the Caribbean, as guidelines. for the way our objects are going to behave. These are going to help guide us through an understanding of basic mechanics. So what we want to try to do is see if we can get to here. See if we can get to this point. Then we want to try to determine if we can find a functional way of mapping between real world and stress world. Because there's also this rather intriguing divide between the real world and the stress world. Now, you guys are probably much too young to have grown up watching Saturday morning cartoons, but when I was growing up, there was always the Roadrunner and Wile E. Coyote, and there was an Acme everything. Well, there is not an Acme stress gauge. Stress is not something that we have a functional way of measuring. We can measure pressure. We can measure some other things and have that as a proxy for stress. But we can't physically go in and have our little proto. I wish there was an iPhone app where you could go in and just lay the iPhone on there and have it say, oh look, the stress is 1.35 gigapascals. That'd be great. We can't do that. So we want to begin to try to understand a little bit about stress, a little bit about what a stress field would look like, and we have some common sense knowledge of that. And so, yeah, let's imagine. Now, do you guys know what Godzilla is? A huge monster that destroyed Tokyo back in the 1950s, and then came back and went through several iterations of being killed and coming back and becoming a nice guy, saving from Mothra and all these other things. And so we're going to have Godzilla. This is a object. This is a material body. So Godzilla's going to be outside the door here, pushing on the door, trying to get in, pushing on the door. And if we think about this, as Godzilla is pushing on the door, will the stress in this material body change? Will it vary? Will Sage feel the same intensity of stress that Harley feels? No. There's going to be a tremendous variation of the stress field within that individual system. How can we try to begin to understand that? How might we actually measure that in the system? Well, that mathematics gets a little bit crazy. So we're going to take a beginning of that. Just keep in mind Godzilla's out there. He will go away by the end of class, so you don't have to worry about being attacked by Godzilla when you leave. So let's start a simple analysis of stress. So when we look at a system, we're going to define a traction or a tractive stress as some force acting on some area. Okay? Perfectly simple. A force acting on an area. What that tells me is that, remember, Godzilla is out there pushing on the door. That means if I have a coordinate system, and we can make it a right-handed coordinate system, a left-handed coordinate system, you can do all sorts of crazy things. Yeah?
Sorry, does this imply that there are other forms of mathematically representing stress if tractive is just force over area?
Yeah, we're going to end up with Cauchy. as our preferred form. So if I
Our
have,
units won't change, right?
we're going to shrink area to 0. Okay, bear with me. Because in calculus you learn this magical little thing called the unit. So if I have an area, and let's make this ridiculous. So this is A. If I have a known area, if I have a coordinate system here, there's my coordinate system. If I have a known A, what I can do is I can go around the room and measure what my force is acting on this area and begin to map out in X, Y, and Z what my component of stress is going to be like throughout the room. I know that because we have some simple rules, if I have a general traction here, I can talk about components that are perpendicular to that plane and components that are in the plane. So I can talk about a normal component, where the normal component, can we do away with Newton? Actually, we'll never be free of Newton. So if I think about a plane normal, do you know what we're talking about when we use the term plane normal? A plane normal, effectively, you can think of it as the direction, the vector, that is uniquely perpendicular to a plane. That is, in other words, no matter where I measure, this angle is always 90 degrees. If it's tilted like this, I have a couple of occurrences of 90 degrees, but then everything else is off. And so a plane normal is uniquely perpendicular. And when I have a plane, if you get into representing this system in vector sorts of systems, the length of this plane normal will vary given based on the area of the plane. Okay, fair enough? So I have a normal stress. And I will have a component in this case that I'm going to call shear stress. And the shear stress is within the plane. So, as I take my A card here, if I have my coordinate system, I can sit here and look at the result of Godzilla's actions as a normal component to this and as shear components in the two other directions. Does that make sense? So if I wanted to fully describe the stress within this particular object, I would have to measure, this is going to get very monotonous, all the way along, come back and go, okay, now we have this. Oh, now we've got to go the other way. At every place in the body. And I would have to carry this card with me at all times. Well, imagine if that's all we were limited to. So you go to class and you know, let's say that you have a class with Dr. Engel in the English department, and instead of listening to the discussion about Shakespeare, you're sitting there with your A card and you're measuring these different things. You know, Lars is going, and Lars is a very patient man, but he might get a little bit unhappy with you carrying the A card around and always trying to measure. So we need to find a better way to do this. But let's first look at some of the consequences of these simple characteristics. If we were to extend this into an XYZ coordinate system, we could imagine a cube. We can carry a cube around with us. Now let's change that angle a little bit to look better. Okay? If we, instead of using this plane, if we could have a cube, then we could define several components of traction. So we've got some general traction in this system that we're trying to describe. And what we're going to do is we're going to describe in terms of face and direction. Now, for this simple sort of a system, I use a coordinate system that probably will drive you crazy, that you'll hate. I'm going to call that direction X. I'm going to call this direction Y, and this direction Z. If you would prefer, we can go 1, 2, 3, and have it be some sort of irregular coordinate system, but just X, Y, and Z. So if we have a general traction, remember Godzilla is still out there. Godzilla is not scheduled to leave until 9:50. So if we look at this particular system, I know that on each face of the cube, I'm going to have a normal component and I'm going to have shear components. Okay? So I'm going to start over here, simple. And we're going to call this one TXX. This being an X normal face of my cube. This is a Y normal face, and this is a Z normal face. Okay? I have a TXX acting on the X face in the X direction. All right? We're good? We will have a TYY. Oops, that's a good, yep, okay, I rotated. It's a terrible thing about getting old. Coordinate systems tend to just merge into sort of meaningless blather sometimes. TZZ, and I've got a TYY. Likewise, I'm going to have a TXZ. Do you see that? It is on the x face acting in the z direction. I'm going to have a t x y. I'm going to have a t y x and a t y z. Are we good so far? A t z x and a t z y. So I have 9 components. So if we list, so we've gone from this simple definition, talked about shear components, normal components, plane normal components to our system, to now what we have is we have txx, txy, txz. We have here, and I'm going to put these into a specific order. Hopefully it will make sense a little bit later. So let's have a tyx, tyy, tyz. Let's have a tzx, tzy, tzz. Now I put them in a specific form, just to kind of keep things simple. Where I have the same direction in each column. And I have the same face in each row. Okay? So that if I look at this system, this has the characteristics of a 3x3 matrix. Where we're looking at face direction, face direction, face direction each time in here. Face direction, and we have something intriguing. This diagonal is our normal. Our off diagonals are shear. Good? Yeah.
Are you saying those specific exactly TX or TXY,
Yeah, all of these
Those
off diagonals,
specifically-
these are shear components.
So like just the things
They are, because the way that I set this up was a 3x3 relative to the coordinate system that we were using. Because we superimposed, Angelina, we superimposed this on a rectangular Cartesian style coordinate system. And so I put this into the order that we're going face direction, face direction, face direction, and I clumped all of the face in this column, and the directions in the, in the rows, and the directions are the columns. So that puts the diagonal as being the normal components. My off diagonals are the shear components. Now, if you've gone through some of the mathematics here, you will recognize that here we have 3 equations, but we have too many unknowns. We have 3 equations, 9 unknowns. That's not very nice. That's going to take a while to solve. So we want to try to find a way to solve that. we want to see if we can simplify this in any way. Now, we have to go back to Newton, and we have to think about the way a continuous material will behave. Let's imagine that our material body is a series of cubes. Cube after cube after cube after cube. Each one's going to resolve out normal and shear components, right? Well, if xy is not equal to yx, what happens? It wants to rotate. If yz and zy are not equal, they want to rotate. So we can't have that. That would be very weird. You know, imagine that in the course of a simple day, a portion of your body decided to just start rotating for no reason. Ooh, that would hurt. So for continuum systems, we can't have that. They can't behave independently of each other. And so we can rephrase this, we can simplify a little bit. Txy, Txz. This one is going to be Txy instead of Yx. All right, put that Tyy, Tyz, Txz, Tyz, and Tzz. So now we have 6 components. They're equal. Those two are equal, so we can just simplify. This says Txy equals Tyx, Txz equals Tzx, Tyz is equal to Tzy. So now we have 6 components. But we still have a problem. We still have a cube, and it's a finite cube. It would be like trying to carry one of these boxes around in your pocket all the time. This is not going to be fun. But if we go back to Calc 1, Calculus 1 gave you a little bit of magic called a limit. And it's not like when your parents say, "I've hit a limit." If you think about a limit, if we look at this T over A, what we can do is define stress. Stress, sigma, is the same as the limit of force acting on an area as area approaches 0. We can take a limit. We can shrink our cube down to a point. This is called Cauchy stress. Stress at a point. So instead of having to carry your A card with you, instead of having to carry a cube with you, you can have a point. Cauchy stress, stress at a point. Put that in your pocket, and you've always got stress with you. But it's a good kind of stress.
How do you spell Cauchy?
This would be Cauchy stress. Stress at a point. So now, if someone asks you if you're under stress, you can reach in your pocket. There it is. You want to know what stress is? This is stress at a point. This is Cauchy stress. The limit as the area approaches 0 at 4 seconds. And we're going to change our symbol. Godzilla's gone. going to change our symbol to a sigma. And then try to move forward from there. So are we good? All right.